18.
Il fait 26 dans les couloirs. Il fait 26 dans les couloirs.
26 dans les couloirs. Ah bon, c'est là, apparemment, il fait 18.
Ouais, ici c'était beaucoup plus frais quand on a ouvert. Mais les chauffages.
Il marche le chauffage? J'ai tourné le bouton. Il était fermé là, puis j'ai tourné le bouton.
Tu regardes si ça fonctionne?
Bah, il s'est mis à fonctionner la semaine dernière.
Il y a 2 semaines que.
Ah, moi ça va parce que je mets ma JT, les gens peuvent rester assis.
Oui, parce que là c'est éternellement en 0.15.
Tu le sais?
Regardez la même.
Jérémy, tu dois chauffer la salle.
Collectivement. Bonjour et bienvenue pour cette session du séminaire de physique mathématique. Aujourd'hui, nous avons le plaisir d'accueillir Philippe Biane qui va nous parler de processus d'exclusion simple quantique et cumulant libre. Il y avait une question, do you prefer the seminar to be in, does someone request English for the seminar? Yes.
Yes. Okay. So I will speak English, and I thank Jeremy for the invitation. It's the first time I'm here, actually, in CEA in Saclay, so thank you. So my talk will be about quantum version of the exclusion principle and some connection with free probability. So maybe not everybody is familiar with free probability. I imagine most of you know a lot about exclusion process, actually, certainly much better than me. So I will maybe focus more on the free probability things. Okay, so this started about 1 year and a half ago when I received a message by Denis Bernard. He showed me some nice polynomials and asked me whether I could find a formula for these polynomials. And he knew how to compute them by some recursive scheme, and asked me. So I will just write a few of them. The first few of them. So these polynomials are indexed by circular permutations of 1n, and they depend on n variables, x1, x2, xn. So I write the ones on. So this is x1, x1 minus 2, x3 minus 3, x2. And this is equal also to q1, 2, 4, 3. And finally, 1, 3 to 4 is x1, 1 minus x3, minus 4 x2, plus 5 x2, x3, and minus x4. Okay, so these polynomials seem to have nice properties. They seem to have integer coefficients with some signs that you can predict, and they are of degree 1 in each variable. And moreover, if you compute some more, I will not write them down, but if you compute some more, you see some nice features, like, for example, some terms, these terms are 1, 2, 5, and the next one is 14, and you guess what it is. And if you take the sum of absolute values of all coefficients, you get also a nice set of numbers which can answer a lot of things like bases of the associated graph or Schroeder numbers. So these polynomials seem to have a very nice combinatorial structure. My aim is to first I will explain where they come from, and then I will explain how to compute them. I will give an explicit formula, and I will explain that they have some connection with free probability. These polynomials they can be expressed in terms of free cumulants, and I will explain what are free cumulants. Okay, so where do they come from? So they come from the quantum version of the exclusion process. So the exclusion process, you have particles on an interval on a line, and the particles can jump to at each step either to the left or to the right, so it's continuous time. And we have the exclusion rule that a particle can go to the if there is a particle somewhere, it can go to an empty place, but it cannot go to a place which is already occupied. And there are some particles coming. So here I will look at the exclusion process, which is symmetric, so there will be a 1/2 probability. And there are some rate for coming and going out at the end of the interval. Okay, so this is a very well known and studied model. Lots of works were after. So my aim is to consider a quantum version, which was introduced in the physical literature some years ago. And the quantum version uses Hamiltonian, which is the following. So here, the CI and CI dagger, they are the usual creation and annihilation operators for fermionic particles on the line. Index, so I is indexed by the sites on this interval, say from 1 to n. Yeah. And the W's are complex Brownian motion, independent Brownian motions. Okay, so this is Hamiltonian. So the state space, of course here the state space is plus or minus 1 to the n, if you, okay, maybe 0, 1. So the state space are just, you say whether you have the site is occupied or empty, and you put 0 or 1. And of course here the state space is the quantum version, that is this, and the creation and annihilation operators operate on this space. And so there is another way to look at this, which is to look at the following Brownian motions on n dimension. So you look at n by n Hermitian matrix, and you put complex Brownian motion just above the diagonal and below the diagonal. So this is a Hermitian Brownian motion, but it's not the usual Brownian motion because there are zeros outside the two diagonals. Okay, so it's a hypoelliptic version of the usual well, the hypoelliptic version is, let me call this W. And so DWT, UT, so if we look at this differential equation, it defines a Brownian motion on the unitary group. And now this unitary evolution describes this process when you don't have the outside particle. Just when you look at the number of particles is fixed, there is no entrance and no. Okay. And now so this is n-dimensional Brownian motion here, but you can look at its action on the sum of on the exterior Fourier of t to the n. The case exterior Fourier corresponds to the space, the state with k particles. Okay, and this unitary Brownian motion acts so this is a decomposition of this space. Okay, you can write this space in the following way, according to the number of operators associated with the particles with the creation and annihilations. Okay. So when you have this this evolution, you can write the evolution for if you start from a state rho, that is a density matrix rho on this space, then you can let it evaluate like that. And now the equation is okay, you have a stochastic equation which gives you the evolution of the state, rho t, which is the following one. Where here I have, of course, I have a product of 2dh. This means that I have to use the Ito formula to make sense of this. Okay, because I have the h essentially is a Brownian motion. Okay, so we have this stochastic differential equation which gives you the evolution of rho. Now you can write a stochastic differential equation which takes into account the boundaries. I will not write it down. I will just. Okay, so that's the right one. Okay, so. So if you want to take into account the outside, so to let particles come in and come out, so you have to write down the boundary terms. There is a well-known way to do that, which is it's called a Lindblad operator. So I will not describe it here because I don't really need to describe it in more details. You can have a look at the literature if you want to see it. But now this is the model. The model is that. So we have a density matrix, rho t, which is a random density matrix. Okay. So we have a random matrix of size 2 to the n. Okay. But actually, all the information in this random density matrix is contained in the correlations. So the correlations are the matrices. Gij. So this is n by n matrix, and actually from this matrix you can reconstruct rho t because essentially it's I don't know how you call this coherent state. I don't know what is the right how do you call this? Coherent state, is that the right way to call it? Maybe, I don't know. Okay, so essentially it's a fermionic analog of a Gaussian matrix, so it's completely determined by its correlations. Okay, so we have a 2 to the n matrix, but actually its information is contained in this random n by n matrix. Okay, and now what people who look at this model are interested in is to compute the cumulants of these. Yes?
You say it's a free fermionic model.
Yeah. That's I don't know how you call this in physics. So.
This is apparent from HT that it is a free fermionic, but about the Limblap, it does not hide the...
No, it's a linear term.
It's linear.
It's linear. So it doesn't break the fact that it's free fermionic. Yes. Of course, they generate the Lie algebra of the unitary group, and you add a linear term, so it remains free fermionic. So everything is contained in the correlation. So what we want to understand is the cumulants of these variables. Okay, so we want to, you call this connected correlation functions, is that right? Or okay, so I will write this PC of Gi1J1 Ik. So you take a k of these numbers, random variables. So what we have is a model where we have constructed a random matrix of size n. Okay, and now we want to understand the correlations of these things. These measure, of course, the correlation between what happened at size a and at size j. Okay, and now. It turns out that this is of the order 1 over n to the k minus 1, and when n goes to infinity, so we let the size of the interval go to infinity, and there is a non-trivial contribution only if J1 Jk is a circular permutation of I1 Ik. Okay. Well, this comes from the analysis of this model, and so what we want to understand is the following. So So I take n numbers, I1, I2, Ik, and I put them in a circular. So I want to compute this. So the cumulant of Ji1, I2, Ji2, I3, Ji3, I4, etc., Jik, I1. Okay, and now this is. Like 1 over n to the k minus 1, g of u1 uk. If I assume that I1 over n is like u1, I2 over 2 over n is like u2, etc. Ik over n is like uk. Okay, so I let my number of size go to infinity with n. And I assume that there are some numbers, I1, u1, uk, real numbers between 0 and 1, such that I1 over n goes to u1, I2 over n goes to u2, etc. Okay? And then, in this case, I have a function g of u1, uk in the limit. Okay? Now, it turns out that this function j is piecewise polynomial. Okay? So that's where my Q polynomial will appear. So G will be a piecewise polynomial function. So you can, it is polynomial in each of the sectors where you have some ordering of the UK. Okay? So in each sector, when you have a permutation sigma, in each of these sectors, it will be a polynomial. Okay. And moreover, the polynomials will be such that, so instead, of course, it will be invariant under circular permutations of the U's, by definition, by the formula. Okay? Clearly, it's invariant by circular permutation of the U's. So instead of looking at all the permutations, you just need to look at permutations up to circular permutations. Okay? So instead of looking at one function g in each of the sectors, you can look at several functions. G sigma will be defined on u1 smaller than u2 smaller than uk, and sigma will just be and sigma will be a circular permutation. Okay. So I can just as well restrict to this domain and say that when I make a permutation of the U's, I get another function g, which depends on sigma. Okay, and well, the g sigma are essentially the q which I have, except that I change the name of the variable from x to u, but that's all. Okay, so that's the definition of the, or if you want, a way to find the polynomials q's. Okay, and there is a set of now there is a set of equations that you can. Yes.
You didn't specify what is the boundary.
They are all between 0 and 1, of course.
No. I was before about your model. You wrote.
Oh yes, you have.
Process, you had alpha, beta.
It's contained in the that equation. So I have alpha, beta, gamma, delta. There is an overall scale which depends on alpha, beta, gamma, delta, and I put this overall scale to equal to 1, if you want. So it really, there is some dependence on this alpha, beta, gamma, delta, but it's I just forgot the dependence. I mean, it's a trivial. Yeah, yes, it's yes. It doesn't really affect the. Okay. Okay. Now, what do the Q sigma satisfy? Okay, so Q sigma is of degree 1 in each variable. I don't forget any. Yes. So the first values are these ones. Q1 are given by this, and Q1, 2 are given by this. And in general, you have Q sigma is x1, P sigma of x2, xk minus 1 times 1 minus xk. So the polynomial vanishes for x1 equals to 0 and for xk equal to 1. Okay. So all these you can check on these formulas, of course. And there is a continuity condition, which is that if you look at Q sigma on the hyperplane xi equal to xi plus 1, okay, you look at one of the hyperplanes which bounds this simplex here. This is equal to Q si sigma si at xi equal to xi plus 1. That means that when you look at the boundary where you exchange the variables xi and xi plus 1, if you conjugate sigma by si, so here si, of course, it's just the permutation, the transposition I plus 1. Okay, so when you look what happens at when you cross the boundary, of course, it has to be continuous. That's just this continuity. That's clear. And now the most important condition, so all these conditions are not so difficult to understand. The most interesting condition, of course, is what happens when you cross the boundary. How does your polynomial here you can see, for example, that when you go from 1, 2, 3, 4 to 1, 3 to 4, so you have exchanged 2 and 3, and you see that the coefficients, for example, here of x2 and x3, they have changed from 2, 3 to 1, 4. Okay, so something is happening here. So what is happening at this point? So we have to specify this. So I'll try to, yeah, so you have a permutation sigma, you have the other permutation where you have exchanged the role of I and I plus 1. Oh. And you have to say what happens between the two polynomials. Well, because of, let me call Q sigma A plus xi b plus xi plus 1c plus xi plus 1d. Okay? I can always do that because say A, B, C, D are polynomials in the other variables. So this is just because it is of degree 1 in each variable. So I can always leave this extension. But I can do the same for the other permutation polynomial. Now this condition of this continuity condition tells you that A is equal to A prime, okay? D is equal to D prime, and now the sum B plus C is equal to B prime plus C prime, okay? So now if I want to say how to pass from sigma to SI, sigma, SI, so when I cross the boundary between two simplices. So I have to say, I have to give you an equation. So the equation is the following. So I'm trying to, I will write it this way. So the coefficient of xi in q sigma plus q si sigma si, so at xi equal xi plus 1, is equal minus the coefficient of xi plus 1 in q sigma plus q si sigma si at xi equal xi plus 1. This is 2. So this is given by 2. I will explain in a minute what this means. Okay, so what do I mean? I mean that sigma, you see that sigma is a cyclic permutation, circular permutation. So when I multiply it on the, so here I could put it on the left. So A psi sigma, I can write it as the product of two permutations, two cycles. I have a cycle, cyclic permutation, I multiply by a transposition. So this splits the transposition, the permutation. Since you want this is my permutation.
You mean SI sigma?
Oh yes, sorry, SI sigma. Okay, so I is somewhere. I plus 1 is somewhere on the cycle. So this is sigma. And when I multiply on the left by SI, what I do is that the point which is just before I gets mapped to SI plus 1, and the point which is just before I plus 1 in the cycle gets mapped to I, so I just, the cycle is divided into two cycles. Yes?
What do you mean by coefficient of xi? You mean the b, or you mean the monomial xi, its coefficient in the polynomial?
No, the polynomial is of degree 1 in xi, okay? So I just take the coefficient of xi.
Okay.
So it's a polynomial in the other variables, okay?
Why do you specify then xi? It's no longer a polynomial in xi, so you cannot. Why do you specify?
I will just show you the formula. So the formula is just, let me just be sure I make no mistake, but so b minus c prime is equal to b prime minus c is equal, so if I call this delta, so this polynomial here, delta, it's a product, so first, so I call this sigma plus, but that's the part of the cycle which contains I plus 1. This is sigma minus, the cycle which contains I, okay? And the variables x minus are the ones which appear on this cycle, okay? The variable x plus are the ones which appear on this cycle, okay? And so these polynomials are well defined, and they are polynomials in all the other variables apart from xi and xi plus 1. It's a product of two polynomials, one in these variables and one in these variables, okay? And now, what I say is that this is equal to delta. This is the meaning of this, if you want, okay? Is that clear? Or?
I'm a little unclear what you mean by x minus in front of the coefficient of x to the right. Yeah, that first x minus, what do you mean there?
I have some numbers here.
Yeah, but what do you mean by the notation parentheses x minus? I mean
so this is a polynomial. So sigma minus has some variables.
Right.
Okay, it has a certain number of variables, and I take these variables minus. They are not numbers from 1 to k, but they are ordered, so I can always imagine that I reorder them from 1 to k, and that's all. Yes.
Did you use about setting xi equals xi plus 1 in the formula, and then you take the coefficient of xi?
No, you take the coefficient of xi, and then you take, well, okay. If it's not clear, you just take, this is well defined, and you take this as a definition. And this is equivalent to this if you want, if you prefer. Okay. Yes. Because I mean, okay, it's easier to state it in this way. Okay. But it's equivalent to. I mean, I don't want to explain this because I will be wrong at some point and will not be happy. So just this is non-ambiguous. Okay. With this definition of delta, so you can forget that. Okay. So. And now, so this tells you that if you know the polynomial q, for example, for this cyclic permutation, 1, 2, 3, 4, 8, k, then you can get all the other polynomials by using these contiguity relations. Okay? Yes?
Can I think of these recursion relation as like in random matrix models, as a loop equation? When you take the large n limit, you compute correlators, you can split them.
I'm not sure about that. I don't know. So these relations were derived in a paper by Bernard and Jean some years ago. They are based on essentially on the Ito formula for that you take the limit and you use Ito formula. So I'm not sure whether they are related to what you say. I mean, it's not clear. I don't know, but I'm not sure. Okay, so they are based on the Ito formula essentially. That's which is really what is.
Is there a simple way to see why many are equal? Because like there's a singleton and you split.
Why?
Why many of them are equal? Why?
No. Well, there are some symmetries that are more or less obvious. But when you go to higher, less and less are equal. I mean, there are some obvious symmetries, like when you reverse and when you take x, go to 1 minus x and things like that. So because of these symmetries, when you look at small degree, small polynomials, many of them are equal. But when you go to higher orders, and I mean, the number of different polynomials goes like n factorial. So it's really accidental. Not really. I don't think it's really meaningful. Well, I think I can tell you that, for example, I don't think I have them here, but okay. So already, if you look at 5 at the other. At 5, you have much more polynomials which are different. Okay. Okay. So now of course, when you see that and you see the, it's not trivial, but it turns out that all these conditions uniquely specify the polynomials. Okay, so you can forget about where they come from and just look at this combinatorial problem. Can I find a formula for these polynomials? Okay. It turns out that you can find there is a nice combinatorial way of expressing this formula. Okay. So, and this combinatorial expression, well, you can somehow come to it by some numerology, because you just count the number of terms here. You just sum all the coefficients and you find Schroeder numbers. And Schroeder numbers are numbers which are very common in combinatorics, and they count Schroeder trees. So I will explain what are Schroeder trees. They count many things, but in particular they count Schroeder trees, which is the thing that I use to find a combinatorial formula. So a Schroeder tree is a planar tree. With a root, and such that, so in a tree you have internal vertices and you have leaves. In a Schroeder tree, all internal vertices have at least two descendants. See, this is a condition which defines a Schroeder tree. So here you have a Schroeder tree. So yes, I should put this like, okay. So you see the root is an internal vertex, and you have here 3 internal vertices. And you see they are all at least two descendants. Okay. And so the number of Schroeder trees, it's called Schroeder numbers. And it turns out that Schroeder trees are in bijection with a nice object. So let me draw a polygon like that. And let me consider a dissection of the polygon. So, for example, this one. So this is something which is also a very well-known combinatorial object. By a dissection of a polygon is just a set of diagonals of the polygon, so which I have two vertices and a diagonal between the two vertices. A set of diagonals which do not intersect. If I take a set of such diagonals, this divides my polygon into polygons. Okay, so it's a dissection. The maximal number of and to this I can, so I assume that here I have put so I number my at the base I put the numbers n and n plus 1. I have n plus 1 vertices, and so what I do is I take the root here, and I take the dual of this dissection, and this is a Schroeder tree. And now it's easy to see that the whole Schroeder tree gives rise to the dissection of the polygon in this way.
N is the number of leaves.
N is yes. N is the number of leaves, and I don't. There is a leaf. Okay, there is a boundary here behind, but here the number is n is yes the number of leaves, and n plus 1 is the number of sides of the polygon. Okay, and okay, so sets of the sets of diagonals, non-intersecting diagonals of the polygon, they form a simplicial complex which is known as the associahedron. Okay, it's a very well-known object, and it's clearly in bijection with Schroeder trees. And of course, if you take the maximal number of non-intersecting diagonals, what you get is a triangulation of the and the number of triangulation is a Catalan number. It's also the number of binary trees. And if you take a binary tree, what you can do is you can contract. So, for example, let me show you on this simple example. I just here I have 3 descendants. So what let me put, for example, another. Yes. I should obtain this one. Okay. Okay. Yes. Okay. So this is a binary tree. And now if you take this edge between 2 internal vertices, you can contract it, and you get this Schroeder tree. And every Schroeder tree can be obtained by contracting some internal edges. This is clear here because you can start from a triangulation. You can take out contracting edges. It just corresponds just to taking out some diagonals here. Okay. And okay, so we have a very nice combinatorial object, and it turns out that we have a formula for the polynomials Q sigma in terms of this combinatorial object. So for this, what we do is we take a Schroeder tree. Okay, take a Schroeder tree like that, and now these Schroeder trees has what I call corners. Corners are the things that are between 2 successive descendants. Okay. So, for example, here I have corners. So I can enumerate them, and let me put some numbers here. So first I will put the numbers in the order, in the usual order, like that. Okay. Okay. And then what I do is that, so I will make a picture with the same. Okay, so now let me make a permutation of the numbers from 1 to 9 here. So 2, 3, 5, 7, 1, 6, 8, 4, maybe 8. Okay, let me take an arbitrary permutations, and let me associate to this a polynomial in the following way. What I do is that I looked at each internal vertex, okay, and at each internal vertex, I looked at x indexed by the minimum of g. So this means that, for example, here I have 3 and 1. So I put an x1. So here I will show you, and I will put a product of minus x2, minus x1, minus x5, minus x6, minus x8, minus x4 minus x9. Okay. So I associate to each of these trees a monomial like that. Okay. And this monomial is obtained by looking at all the internal vertices, and for each internal vertex, I put minus x indexed by the smallest number which appears.
Is 9 different from 1 and not counted with 1 and 3?
Oh yes, sorry, of course. You're right. I made a mistake. You're right. Thank you. Okay, so the number of terms is the same as the number of internal vertices. Okay. They are all distinct. Okay. And now, suppose I have a sigma circular permutation of 1k. Let L belong to 1k. So what I do is I take, so what I claim is that Q sigma is equal to the sum over all trees, not all trees, but only all prime Schroeder trees. So what do I mean by a prime Schroeder tree? It's a tree such that the leaf on the branch on the right is always a leaf. It doesn't go further. Okay, so it's that they are called prime Schroeder trees. That's a technical point, but okay. You have to sum over all prime Schroeder trees, and you take the monomial. So let me the product over V. I don't know how to call this. So W means just that I look at V, and so I index the corners from the left to the right by the numbers from and in the cyclic order given by sigma, and I put L on the right. Okay. I fix L. Actually, this doesn't depend on L. It turns out that this is symmetric on the cyclic permutation. This doesn't depend on L. And this gives me a formula for my Q sigma. And if you have this formula, well, you can check that you actually, this satisfies all the relations that I gave on the in the definition of the Q. Okay. Remember, I have had several formula. Okay, you can check that x1 is always a factor, because I just checked this condition because it's very easy. X1 is always a factor. Why? Because 1 can appear anywhere. It will be always the smallest number in its. So it will always appear in all of these monomials. Okay, the minus x1. So certainly x1 will divide your polynomial. Okay. So the first condition is easy to check. I will not check the other condition. It's a bit a bit messy, but I mean it's not very difficult. But you have to think and understand some properties of these Schroeder trees. Okay. In particular, the fact that you have this. You remember that I had sigma and Si, sigma Si. The fact that there is this relation between the two is due to the fact that you can always put the I here. And so the I plus 1 would be somewhere, and then you can cut your tree. So the I will be on. And then you can cut the tree somewhere and split it into two trees, and they will correspond to the Q sigma minus Q sigma plus. So I will not go do that. I mean, I will not go into details, but yes.
Is K the same as N, or are there different numbers?
Here, oh yes. I did that with K, but it's of course yes. It's a number of variables. Okay. Yes.
So sigma is a given circular permutation, and you use it to label the.
Yes.
To label the
for example, here the circular permutation is 2, 3, 5, 7, 1, 6, 8, 4, 9. So you have an ambiguity when you write a circular permutation as a sequence of numbers. That's why you have to choose some number L from which you start. But it turns out that the result doesn't depend on the L that you choose. Okay?
Is there a way of thinking algebraically of this Q as some sort of determinant or characteristic polynomial?
I will explain you now that they are free cumulants. That's the right way to think about them. Okay, so maybe not everybody is familiar with free cumulants, I imagine, so I will explain what are free cumulants. That's completely, well, it's a rather different story. So now I explained to you the combinatorics of these objects, but now I will try to give some meaning to these objects, okay, because we saw that they appear as limits of cumulants, okay, but actually they are free cumulants. So what are free cumulants? So first, I will first, before defining free cumulants, I will define ordinary cumulants. That maybe certainly you are more familiar with. So they arise when you look at random variables and the Laplace transform and the logarithm of the Laplace transform. You can expand the logarithm of the Laplace transform. I think it's called free energy in physics or something like that. But for me, I'm probabilist, so I call this Laplace transform. You take the logarithm and you expand it as a Fourier series in the lambda. And the coefficients are some polynomials in the moments of the xi. Okay? For example, so I call them Kn. So Kn of x1 is just the expectation of x1. So K1, sorry. K2 of x1, x2 is just the covariance. So expectation of x1, x2 minus ex1, ex2, and so on. So these are what you call, of course, the connected correlation functions. Okay. So this is a usual way of introducing these things. There is another way to look at these things, which is to use a combinatorial formula for them. And this, the simplest way to write down this combinatorial formula is the following: is to say that to express them as the sum of all partitions of the set 1n of k pi of x1, xn. So here, what is k pi? So you have the partition of the set 1n. Say, for example, pi is 1, 3, 5, union 2, 4. So I have a partition of the set 1 from 1 to 5. And then this k pi will just be k3 of x1, x3, x5 times k2 of x2, x4. Okay? And now it's a simple exercise to check that these cumulants here are defined implicitly by this equation. Okay? The product, the expectation of x1, xn, where x1, xn can be any family of random variables, is the sum of the three cumulants, of the cumulants. So the cumulants are so you see that they are expressed as polynomials in the moments, the joint moments of the xi. Okay, and you have an implicit formula, but there is also an explicit formula that you can obtain from this formula by a kind of Möbius inversion of this set of partition, which is a lattice. So the Kn of x1, xn is the sum over pi, the same set of partitions of E pi of x1, x2, xn, and there is a combinatorial factor, which is the Möbius function of the lattice of partitions of the set Okay, I don't need to specify this number here, but there is an explicit formula for this number, which is in terms of product of factorials, okay, with a sign. Okay, so these two formula are inverse of each other, and now the free cumulants. Well, the free cumulants is exactly the same story, except that they are adapted to non-commutative random variables. So this means that I look at an algebra A with a state phi. So phi is just a linear form on A, such that phi of 1 is equal to 1. Okay, A will be non-commutative in general, and so we have so we introduce free cumulants in the following way. We have an implicit formula, which is exactly the analog of this formula, which is here. But here, so remember that the A don't commute. And here, instead of summing over all partitions of the set 1n, we sum over all non-crossing partitions. So what are non-crossing partitions? So in order to define what are non-crossing partitions, I put my numbers on a circle. Now it will be very important that since things don't commute, we have to take care of the order of the numbers from 1 to n. So we put them on a circle. Actually, only the cyclic order will be important, but okay. And so a partition of this set 1n, it will be non-crossing if when I draw the parts of the partition, say for example I have the part which is equal to 3, 5, 7 here, another part which is equal to 2, 8. When I draw the polygons given by the whose vertices are given by the parts of the partition. So this partition, for example, contains 1, 2, 9, 3, 5, 7, 4, and 6. Okay, it has 1, 2, 3, 4, 5 parts and 8. Yes. It has 6 parts. Okay, and the important fact is that when you draw the polygons, you can draw the polygon corresponding to each part, and this polygon have to be non-crossing. They cannot cross inside the. It's a bit analogous to what I had for the RCL slide, but it's quite a different object. Okay? So when you do that, well, you define implicitly some linear forms Rn of A1 and An. So these are free cumulants. They were introduced in the beginning of the 90s by Speicher in order to deal with free probability theory, the free probability theory of Wolfskin. So I will not go into what is exactly a free probability, but let me say that these objects are very important for understanding the spectral behavior of very large matrices. Global spectral behavior. I mean, things like density of states, not local behavior, but global behavior for random matrices. For example, if you take two random matrices, you know the spectra. You want to know what is the spectrum of the sum. Well, you can compute the spectrum of the sum. When they are very large and independent, the spectrum of the sum depends only on the spectra of the two matrices. It's a law of large number. And the computation is not easy, but it can be done using these objects which are here. Okay. Now there is a formula.
Sorry, I have a question. What is the difference between crossing partition and the dissections of a polygon which you?
It's not the same thing because I asked that my in the dissection I asked that the what do you say well it's.
Okay, yeah, I see.
It's not the same thing. Of course, if you take maximal dissection, it's given by binary trees, so it's counted by Catalan numbers. These objects are also counted by Catalan numbers. Certainly, there are bijections between them.
Okay, it's because.
But it's not.
When you have 3, 5, then you also need to have a diagonal 3.
Yes.
You always have to have a full.
Yes, there are different geometry. It's not exactly. Okay. there are some connection between the two, but yeah, if I don't know how much time I have. Is it,
5 minutes.
5 minutes, okay, it's enough. 5 minutes is now a connection between free cumulants and classical cumulants. What I call classical cumulants are these. So take a random matrix of the following form. You fix the spectrum, lambda 1, lambda n, and you rotate it by a unitary u, which you take with a Haar measure. So it's a random matrix. That's the most random matrix that you can find, but you are given the spectrum, lambda 1, lambda n. So now you assume that the density of states converges. So this is mu is the probability measure. So you can consider a random variable with distribution mu. So you can compute the cumulants of mu. And the free cumulants of mu. Let me call them Rn of mu. So in this case, this corresponds to the case where A is just the algebra generated by one random variable, x, and so there is only, all the A's are equal, and I look at Rn of A, so this is a sequence of numbers that I call the free cumulants of mu. And now I can look at the, let me call M this matrix, M11. I can look at the classical cumulants of M11. So it is just the upper part, the upper corner of my matrix, M11. Okay. Now the classical cumulants of M11 are like, so it's n to the, I think it's, it should be 1 minus n. Okay. So the distribution of this random variable, you can compute the distribution of this random variable n11 by using the Dissection formula. Okay, and asymptotically, when n goes to infinity, they are asymptotic to. I think there is a 1 over n. They are asymptotic to the free cumulants of mu. So there is a connection between the classical cumulants of some coefficients of a random matrix and the free cumulants of the density of states of this matrix in this way. Okay, and this can be proved using essentially the Dissection integral. Okay, and now a formula for Q sigma. So what I say is that Q sigma of x1 xn is Rn of okay, where so there is a very, very simple formula for the polynomials Q sigma. You want to evaluate Q sigma x1 xn. Actually, they are the free cumulants of a family of random variables, and this family of random variables are very, very simple. They are just indicator functions. Indicator function of the interval 0x, so ix is the indicator function of the interval 0x, where x is some number between 0 and 1. And 0, 1 is endowed with the Lebesgue measure. So this, if you think of this as a random variable, this random variable is just takes values 1 with probability x and takes value 0 with probability 1 minus x. So it's very simple random variable. Okay, just indicator function of the interval 0x. So when you compute the free cumulants of these random variables, so by this formula, you get these polynomials. Okay, so again we have a model where we have classical cumulants of a family of random variables indexed by, which we get by some random matrix, and the limit is are free cumulants of some random variables. But it's here we had only one variable, but here we have a whole lot of variables. Okay. So that's what is quite amazing is that these random variables, they all commute in particular. Okay. So this is quite shocking because free probability, these things come from free probability. Free probability is supposed to deal with objects which do not commute or are very, very little commutation relations. So it's quite shocking to see that. Of course, you can evaluate them on commutative objects if you like. I mean, because the definition doesn't require that they are not commutative. It's just that you don't expect that it has any meaning to compute them on commutative objects. But here we see that very naturally there is a very natural problem associated to the exclusion process, where this when we have to evaluate free cumulants on commuting random variables, and this is something that I don't understand. I could do the computation, but I don't understand why. I mean, it's actually it was a shock to me to realize that these free cumulants. I did not realize it at the first time. I had this formula with Schroeder trees, but then I looking at this formula, I realized, but these are free cumulants. I've been working for 30 years on free cumulants, and they just come to me by some miracle. Okay.
The problem here is that free cumulants are adapted to non-commuting variables.
Of course.
This is commuting.
Yeah, this is very surprising. Yes. And I think I will stop here. Thank you very much. And, but of course, yes.
So you had two formulas for Q sigma as a sum. Is that a bijection between prime Schroeder trees and these?
Oh yes. I mean it's quite easy. If you have a Schroeder tree. So unfortunately I erased all my trees, so I have to write that one of them back. But if you have a Schroeder tree, let me draw a tree like that. Okay, so you put the numbers 1, 2, 3, 4, 5, 6, 7, 8 here. Okay, and now you look at the partition of the numbers from 1 to n, which contains where the parts are given by the corners corresponding to some vertex, okay, some internal vertex. This is a non-crossing partition. Okay, so it relates 1 and 2, it relates 3, 6, and 8. And that's all. It's very easy to see that it is. So that's the reason why you get this formula.
These Schroeder trees were in bijection with dissections of the polygon. Is there a simple bijection between these dissections and these non-crossing partitions?
Well, I showed you how to associate to a Schroeder tree a non-crossing partition. Now you have to come back. If I have a non-crossing partition, how many Schroeder trees do I have? Well, you can see that it's obtained by you take out all the internal things like that, and what you see, you get some. If I have more than 2, okay, you can see that from that there is a formula for the number of Schroeder trees corresponding to a non-crossing partition. It's a product of Catalan numbers, and this product of Catalan numbers turns out to be the Möbius function for the non-crossing partition lattice. That's not obvious, of course, but you can check it. That's the reason why I was able to find free cumulants here. In the free cumulants, you have to invert the formula that I gave here. When you invert this formula, you get Rn in terms of the phi, and you get some Möbius function. This Möbius function is a product of Catalan numbers, okay? And these Catalan numbers, they just count forests here of binary trees. Product of Catalan numbers is the number of forests of binary trees. That's the idea. I mean, of course, I don't give you the details. You can look at in the paper, but that's the idea. But it's all this is quite non-trivial. I mean, you have to do some computation. There is no obvious way why this is true. I mean, you check it when you do the computation, but conceptually, I don't know why you get this. I mean, it would be very interesting to find other matrix models when you look at the cumulants, the classical cumulants, and the limits turn out to be free cumulants or something. That would be very interesting to find other models. I gave you two models, this one and the first with the Dissection super integral, but probably there are other models. But, I think this has not been investigated, and it will be very interesting to look at. Yes, Michel?
If you do something like that, do you expect that discounting, because there were these factors 1 over n,
Yes.
in both cases, which look the same somehow, so you would expect this to be quite a general phenomenon if there is a relation between
yes, because the primitive of the R transform is the integral of the logarithm. There's something like that. It's a logarithm of a determinant something. But I mean, it's very vague in my mind, so I don't want to make more precise statements. But certainly, yes, something like that should be true. Yes.
I missed for your formula. So what is the algebra you are working on?
Oh, it's just you take the Lebesgue measure on 0, 1.
And then you take functions.
Okay? It's a probability space, and these are random variables. They are functions on 0, 1. Very simple random variable, Bernoulli random variables, all commuting.
Yes.
And that's and the formula that I showed you, the Q sigma, are just given by this here.
So you have a collection variables, and they are dependent on each other. They are not independent.
Oh no, they are not independent. Certainly not. No.
the product of two of them is one of them.
Yes. They satisfy some very simple algebra. You take the product of I x, I y, it's I x minus y, x info y. So it's a very simple product.
Okay, so it's a classical probability, but you still apply.
It's a classical probability space that I say they are all commuting. They are very simple, but you have to take the free cumulants, which is something very, very surprising. It's, that I don't understand why. It's really something. And I should say that with Michel, Denis, and the student of Denis, we have used this to recover the large deviation formula of Derrida and about the profile of the exclusion process, symmetric exclusion process, without using matrix, and that's completely different way. And we have even another formula for this large deviation function, which is equivalent to the formula they have, which is not different. So there is some connection between free probability at some point and this exclusion process, which is, but all these remains, at least for me, completely mysterious. I would say. Really...
Other questions? Thanks again.
Thank you.